One. All right. Hello, Ed. Thanks for sending those pictures of Comet Neowise. Right. How's everybody doing tonight? Oh, yeah. I intend to try to find a good view after the show tonight. But I'm a little nervous about the buildings here in Williams Bay getting in my way. Right. I still have to get a telescope out and actually go look at Jupiter and Saturn. I've yet to take the advantage of that opportunity. One second, Katya. I've already noticed an issue.
Oh.
Now they'll be able to hear you. Sorry about that.
So they couldn't hear me before?
No, they could not.
Wonderful. That's okay. Nothing that I said was important.
Alright, we'll wait a couple more minutes. Before we get started. Right. And I think getting a small group of people to go to the South Lawn and look at the comet would be a very fun idea.
Let me know when that happens. I might come up for that.
I'll make sure to give you a heads up. Oh, Alex is on. Thank you, Alex.
Yeah, if you're on right now and you want to just hop into the chat and say where you're from, introduce yourself, that would be great. Hello, Sean. Good to see you again.
All right. I think we've got enough people on where we can go ahead and get started with just a simple tour through Stellarium before we welcome our guest. So first of all, welcome everybody to another episode of the GLASroom. I am Adam, and as always, I have my professional astronomy co-host, Katya Gossman, and we are going to talk about a couple of things to look at up in the night sky, and some things that are going to connect to what we're going to be talking about with our guest in only about 10 or 15 minutes. So with that, we're just going to jump right into Stellarium, and for anybody that's been tuning into a bunch of our shows, I don't have to go over all of the locating stuff in the night sky and Stellarium. If you've watched any of our episodes, hopefully you're able to locate the Big Dipper, as that will be helpful. And as you can see, down in the southern part of the sky, Saturn and Jupiter are already starting to rise at a convenient time to observe them. And right now we're set at only 9 o'clock. So you don't even have to stay up that late to see Jupiter and Saturn now. And of course, as Jeff mentioned in the comments just a moment ago, the real show right now in the night sky is over to the northwest and is Comet Neowise. So one trick that was pretty helpful that I heard earlier in the week was if you find the Big Dipper, just how you normally would take the two stars of the right side of the cup and you would connect those in a line to go and find Polaris. Instead, if you take the bottom two stars in the Big Dipper and connect them, and you draw a line down towards the horizon, will get you roughly in the area of Comet Neowise. Now, there's not too much of as far as bright stars go in that area of the sky, and right now, Neowise is in fact a naked eye object. Katya, what else can you tell us about Comet Neowise?
Yeah, so as you might have noticed, it wasn't always in our sky. It was actually discovered pretty recently at the end of March by astronomers that were using the Neowise Space Telescope. That's what the comet was named after. And currently it is super bright. As of yesterday, I think it was around second magnitude, which for comparison, a star Vega is 0th magnitude. And so it has a pretty parabolic orbit, so it makes a nice parabola while it's orbiting in the sky. And right now it's been visible for most of July, I think all of July actually, and it will continue being visible, at least here in the Northern Hemisphere, probably until towards the end of the month, if not later than that. So go out and take a look.
And one cool thing that you can do here in Stellarium is if you're not able to go out tonight and take a look, you can figure out when the next time you're actually going to be able to, or when next time the weather may allow you to, by going and checking the date and time window. And if you keep going day by day, you can see that Neowise only gets a little bit higher in the sky. Now, it will also get dimmer the farther we go on. So definitely take advantage if you have clear skies tonight. Go out and take a look. Now, there's one other thing that we want to talk about in the night sky tonight, because our guest works at a really cool observatory, and that observatory helped take data for something that came out last year that really kind of was mind-blowing, and we dedicated basically 2 star parties because of it. And over in the southern part of the sky, not exactly the most visible at the moment, but since we have Stellarium, oh, now it's over in the western part of the sky, we can zoom in, and at first glance, it may look like just a normal elliptical galaxy, but the closer you get, and the better images you get, like here. So Katya, tell us a little bit about M87.
Yeah. So M87, we briefly talked about this in our last show, but just to reiterate again, it is a ginormous elliptical galaxy. It is one of the largest galaxies that we found. It has a lot of globular clusters in it. And so it being elliptical, it is very smooth, has a lot of old lower mass stars in it. Um, but it is super cool because it has a super powerful jet that you can see in this picture that's coming out of it that actually emits mostly in wavelengths that the human eye can't even see. So we need to use other instruments and telescopes to find it. Um, and you might have actually heard about this object. It was in the news quite some time ago, like a year ago or so, as boasting the location of the first ever image of a black hole. And so today we actually get to talk to someone who was involved in helping get data to actually take this image, which is super cool.
Yeah, and so without any further ado, we're just gonna jump right in and welcome on Mimi, and we'll let her introduce herself for a second. But I'll change the view. Welcome to the show.
Hi guys, thanks for having me tonight. It's such a pleasure to be here with you. And as you mentioned, you led in with a really exciting result talking about M87 and this really exciting new advances we have in telescopes and imaging to be able to help take the first picture of a black hole. So I'm excited to be here with you tonight and talk about one of my favorite things, which is submillimeter astronomy. But before we go further, I just want to tell a little bit about myself. My name is Mimi Fuchs. I work as a telescope system specialist at East Asian Observatory's James Clerk Maxwell Telescope. That means that I get to work and play with on a regular basis one of the world's largest telescopes, single-dish telescopes dedicated to observing the night sky in these wavelengths invisible to our eyes that are really long, in sub-millimeter frequencies, that are particularly good at imaging the night sky and the cold dust and gas we find in the universe. Before working at JCMT as a telescope operator, I was a telescope operator at another telescope atop Mauna Kea on the Big Island of Hawaii, where I currently reside. And it's known as the submillimeter array. And it was when we'll talk a little bit more about what an interferometer is later on and these really exciting imaging techniques we have. But basically, for the last 4.5 years, I've had the great privilege of operating telescopes that are essentially right on the border between radio and optical instruments on Mauna Kea for the last 4.5 years. I got my Bachelor's of Science from Haverford College in astrophysics back in 2013. And before moving to Hawaii in 2016, I actually had the great pleasure of working in science exams. I've always really loved whenever I had the opportunity to come to Yerkes Observatory and get to work with folks who are very involved with class education. And I felt really lucky throughout my career. I've really been able to work in astronomy, both from the perspective of planetariums and museums, and also now as someone who gets paid to play with telescopes. So I hope that by the end of our time today, you too also feel really excited about this final frontier of the electromagnetic spectrum, and you guys are able to learn a little bit more about this field of astronomy. But this is not just any old conversation, any old presentation. I really hope it's a conversation. So reach out to us, right? You can reach out. Katya and Adam have all the questions. So feel free to interrupt. If something comes up that you want to know more about, let us know.
Perfect. And yeah, I have to say, oh, go ahead.
Oh, yeah.
So I was gonna say, yeah, submillimeter astronomy is something that I think I had maybe heard of in passing recently, but I honestly was not introduced to it whatsoever until recently getting to talk to you and a little bit about what you do.
Totally. And I will say something that I think is very exciting is that, you know, people really were excited about this first picture of a black hole. It wasn't just folks who really like or interested in space. I think everyone can be inspired by the idea that humans came together and achieved something with technology that was beyond our wildest dreams, right? And so I think it's particularly exciting that the first picture of a black hole was taken in submillimeter wavelengths. And I hope that it maybe gets like yourselves and everyone else out there a little bit more curious about why they haven't heard about this field of astronomy very much.
Right. And Katya, I know we have some visual aids, so if we want to, we can switch to that view now and bring that up. Do we want to start right away with the black hole? And if you don't mind, pronouncing the name?
Yes, I would love to. So, of course, we can refer to this as the black hole and 7, but there's a name that has been given that is called Povecchi, which is very special and near and dear to my heart. And it means unbellished source of unending creation. And it comes from the Kumalipo. So this is one of the earliest primordial stories of the Hawaiian creation myth and how we understand it. And so in the first few verses, actually, they reference Po, which is the source of creation. And it's really interesting. I've gone to this really lecture in tandem with a professional astronomer and a professor of linguists and professor of Hawaiian linguists, particularly. And they talk about how cool it is that in the Hawaiian creation chant, there's so much references to the universe and cosmic nuances. Very cool. And so there's a program or a committee that's referred to as the Ahua Hei Anoa program. And when a very exciting discovery comes from the Hawaiian telescopes, they are tasked with giving it a name that's appropriate based in Hawaiian culture. And so Dr. Larry Kimura, Uncle Larry, often known as the father of Hawaiian language renaissance, saw the picture of the first black hole and named it Behi, unending source of embellished source of unending creation. And we'll look at some more pictures of that later on. But I'd like to leave this picture that you folks are showing right here, because this is actually a picture of a star-forming region that we know and love, the Orion Nebula, and what it can look like in submillimeter light. Yeah, so if you wouldn't mind going next slide, I do just want to show you a few photos that I've been able to take snap throughout my career, just to emphasize that a career in astronomy, a career working in telescopes can look like a lot of things. So let's see if this one pops up. Awesome. So I just want to show you guys a few photos of like what my life looks like as a telescope operator. So if you look in the top left-hand corner, this is a picture of the telescope I currently work on. It's, as I mentioned before, it's named the James Clerk Maxwell Telescope. It is the world's largest single-dish telescope that images the night sky and these submillimeter wavelengths. And it's huge, as you can see, nearly 50 feet in diameter. So when I'm running the telescope, I have the great fortune of being able to scan the sky, doing various different projects with this telescope. If you look directly to the right, that's an example of what some of our pictures look like when we use one of our instruments, one of our cameras at this telescope. And to the right is what it looks like in the control room. I have a lot of monitors up to help make sure that my data looks good and that I'm making sure that the facility is safe. And then I get to work with really awesome scientists from around the world. And that is something that is really, really special about my job, that in order to do great science, it requires really great people and great collaborations. So it's really cool that, you know, my telescope is extremely international. We have 6 different partner countries and many other soft partners. And that means we have folks from all over the world coming to help make our telescope better and help take really great science with it. If you look down to the middle, you can see that I have a couple pictures of another telescope that I'll be referencing. This is the Submillimeter Array, another telescope on Mauna Kea that I had the fortune of working at. And to the left is just me at my local library. I'm known as Auntie Mimi, and I do science shows where I travel to different schools and libraries. And I think it's really important to give back to the community and help everyone recognize that they too can work in science. So I feel really lucky that I'm going to be sending this link out to some of my students who I worked with, and they too can get to learn from GLAS education. Yeah. So
Thank you so much.
I'm going to be talking to you for a little bit. Oh yeah, sorry.
Oh, I said thank you so much.
Oh my gosh.
We're very excited to share all this with them.
This is such a pleasure. You guys can tell I'm really excited about this. I really love what I get to do. And I think it's really exciting to get to do these kinds of things, like get on your YouTube show or get to work with the kids in my local library to help other people, you know, find what they really love to do. I hope it could be astronomy, but maybe it's not. So yes, it feels really great to be able to do these kinds of things. And I just want to give you a little bit of an outline from where we're going from here. You know, I feel really fortunate that I work in telescope operations, and I just want to spend the next half an hour with you guys essentially explaining submillimeter astronomy, why it's so challenging, and why it's so important that we have facilities to be able to do this kind of science, and maybe talk about where I hope I get to see it go. So if we don't have any other questions to answer before then I feel like we'll jump right in, and hopefully by the end I'll turn you all into 7mm fans. Yeah.
We're good to go.
Let's do it. Okay, so I'm showing you a picture of what it looks like where I work. This is on the summit of Mauna Kea, 14,000 feet above sea level on one of the world's most isolated landmasses on the big island of Hawaii. Now, I just want you to take a sense of what this looks like. The top of Mauna Kea is very strange. It looks kind of like Mars, or maybe if you've been to some of the Southwest, it looks like these kind of red rocks you might see in Utah. And I want to just bring up this idea that on the top ridge, we see a lot of the world's best observatories. There might be some that actually you could recognize, the Subaru telescope, the National Observatory of Japan, or maybe the classic double domes of the Keck Observatory, one of the world's most powerful telescopes. And see that they all look very similar. They all have the classic R2-D2 look of an optical observatory with these giant domes and these classic light colors that are reflective. But then look down. There's a lot of telescopes that are a little bit different, and they work very differently. And there's a reason there's so many of them there. So I'm hoping that's something that we can start thinking about is, why do we have so many of these telescopes? What do they do? And is it important for us to have them there? Now, I keep using this word, submillimeter. What does that actually mean, right? So submillimeter purely refers to the wavelength of light that we observe at. And they happen to be around a millimeter or submillimeter wavelengths. So the other night when I was taking data with the JCMT, we were observing in both, often we refer to in frequencies, because we're kind of like a radio observatory. So either 230 gigahertz, which corresponds to about a little over 1 millimeter in wavelength, or 850 micron, so a little bit less than a millimeter. This is in contrast to the wavelengths that we see with the naked eye, right, which are on the orders of hundreds of nanometers. But it's not nearly as long as the wavelengths that are used to communicate, say, for the radios that we tune to. It's right in the middle. We're right in between far infrared and microwave. Now, it's really exciting to observe the cosmos in these wavelengths, because we're able to really probe the cold dust and gas that makes up practically everything in the universe. The scientists who apply for time at my telescope, or the telescope I'm fortunate to have, are particularly interested in understanding how stars form, how planets form, almost like taking these cosmic ultrasounds. Now, if submillimeter astronomy is so exciting, it bears wondering why you haven't heard about it, perhaps until now, or maybe until seeing that first picture of the black hole. So I want to emphasize maybe why you haven't heard that much about submillimeter astronomy. The first is how recent it is. So let's think about the history of astronomy in general. Humans have been looking up to probe the cosmos since we've been around, since humans could look up. We've been using telescopes, optical devices, to do it for about 400 years, right, from the time of Galileo. And of course, those were in wavelengths that were visible to our eyes. It wasn't until the time of World War II radio astronomy actually began as a field. And submillimeter astronomy didn't happen until much later, until the 70s. And so I'm going to go into why that is. And so I'm hoping you could help me figure out why that might be by looking at this next slide with me. One more for me. Yeah. I love this picture of the top of Mauna Kea. What do you guys notice about this picture? You guys can write in, maybe Adam and Katya can chime in, but like, what is noticeable? What is striking about this picture to you?
It looks like the view that you get when you're like on an airplane and you've just broken through the clouds and all you see above you is sky, and all the clouds and like atmospheric events like weather and stuff are all below you.
Yes, you feel like you're almost on top of the earth, as if you're on an airplane. You see that you're above the clouds, right? And so that is something that is very obvious to me, is that you don't see any clouds above you, and you can see the clouds below you, right? It is that you've pierced through. And you have a really beautiful sunset. There's sunsets up there are unparalleled.
Yeah, somebody else pointed out seeing snow is not something one might immediately expect.
No,
yeah.
There's a really funny story about this, how when folks tried to order the first snowplow to plow the mountain roads, their order didn't go through. and they didn't realize what happened. They waited for it to be shipped, and they figured it out. And finally, they called back like 4 weeks later, and they go, "Oh, we thought this was a prank. Who would order a snowplow to Hawaii?" And so the only snowplow in Hawaii is on Mauna Kea. It's actually fun. For a lot of the parades we have in town, pre-COVID, we would dress up the snowplow, and we would bring fake snow for a lot of the parades, which is always fun for the kids. And it's true. It's like one of the only places that you find snow in Hawaii. So even though we get snow occasionally, we are at remarkably high and dry conditions. We're at 14,000 feet. And something that's unique about submillimeter astronomy, and one of the reasons why it is so challenging, is that it is really, really affected by the amount of water that is between us and the edge of the atmosphere. So imagine if you were able to standardize a way to do this, to measure how much water is between us and the edge of the atmosphere. And scientists have done it. They often refer to it as precipitable water vapor. If I was able to somehow measure the amount of water between me and the edge of the atmosphere, squeeze it into some sort of source and measure its depth, if we do this uniformly and it's more than on the order of 2 millimeters of water vapor, the signal is deteriorated. You wouldn't get enough to be able to confidently take pictures of the cosmos. And that's crazy. Where can you go on Earth where it's so dry, where there would be less than 2 millimeters of water vapor between you and the edge of the atmosphere? There's only a few places on Earth, which is why we might see optical telescopes a lot of places, even at elevations of close to sea level, 6,000 feet, 8,000 feet. But it's very notable that the places we put submillimeter telescopes, like Hawaii, like Chile, like the South Pole, are places that are very high elevation and very, very dry. So that is one of the first challenges, is that it's very hard to get the conditions where you can actually take pictures of these signals, right? It's like we're right in this middle zone. Optical light, for the most part, totally comes through to our eyes, easy to see. But it's very good that a lot of the radiation, right, there's like some ultraviolet light the atmosphere blocks us from. That's a good thing. But submillimeter frequencies are in that frustrating range where it's very, very much a struggle to work with this atmosphere to get the conditions that allow you to take really good signal. So this is why I feel really lucky that I get to work at a submillimeter telescope, and it's on top of a mountain, and it's really high and dry conditions.
So speaking of being,
go ahead, Katya. I think you were going to ask the same thing I
speaking
was.
of being, on top of a mountain, we have a question in the chat. So they say, I think this is Kate, saying that she went up to Mauna Kea once and she could barely stay awake. So how do you manage? Like, do you have to go up to the mountain to operate the telescope?
That's a great question. Okay, so we moved into remote operations as of November. But prior to that, you absolutely go up to the telescope to work. And it's actually, I find it to be really, really cool because the mountain is my favorite place, and it allows you to acclimatize. So let's say that you are operating the telescope, and you'll operate the telescope from 5 p.m. to 7 a.m. for 5 nights in a row. They will give you a night for your body to acclimatize, because operating at 14,000 feet, you can experience 40% less oxygen intake in your body just due to being at such a high elevation. And so it takes some time for your body to adjust. So usually what I do is I go up the day before and I'll give myself a night of sleeping at altitude. And I stay awake with lots of caffeine and sugar. And good company. You get to work with some of the coolest scientists from around the world. And so they're also there at the observatory with you. And having a good conversation like that can help you stay awake. Now I can work remotely. So if I need to, I can still go up to the summit and work. But I can just go into my office in the town of Hilo and log on to a bunch of the local computers and then control the telescope remotely. Actually, very similarly to the way that you guys do are able to in a lot of your programs.
Yes. All right. So I guess now a little bit back to kind of what submillimeter astronomy really is. So you talked about how it's really difficult because there's only a certain number of places in the world that you can do it. What was the next?
The next one comes in. The next challenge is that there's it is a very, very well, the next challenge comes in a little bit with resolution. So I want you guys to think about if you had to design maybe the world's best telescope, right? There's a reason that telescopes want to be very big in size, and it has to do with resolution, which is this ability to distinguish fine details. And this is not unique to a telescope, to any optical device, right? So think about with the own human eye, for example, right? The amount of the resolution of the human eye, the detail we're able to see, is dependent on two things: the size of our pupil and the size of the wavelengths that our retinas can actually pick up on, right? And so if we wanted to see better resolution, one way in theory the human eye could evolve would be much bigger, right? If we could have much bigger pupils, maybe we'd have better resolution, because that is, we know this relationship of resolution depends on the wavelength of light that we're trying to look at and try to study, and the size of the optical device. That could be the size of our eye, that could be the size of our dish, the size of our camera on our cell phone, whatever. And so submillimeter astronomy is actually in a very difficult position. So I'm hoping you can maybe go ahead to a slide and skip ahead for me. There's one that has some green check marks. Actually, this one's pretty good if you want to stay on this for a second. Okay. I like using this one just as an example, talking about resolution with an object that maybe you're familiar with. So maybe some of you have had the good fortune to look with the naked eye, and you're able to see a little bright spot, which you can identify as Jupiter. You know, if you're able to get a little bit better resolution with a telescope or really good set of binoculars, probably a telescope, you would see something that would be 60 times better on the order. Instead of an arc minute, which your eye can see, it would be 60 times better. And you could maybe even be able to detail on Jupiter, enough detail to see that there's an atmosphere that has a gradient picture to us. And essentially, you can get to understand this idea that we can continue to strive towards better resolution. So can you skip ahead for the next slide for me, please? Yep. Let's say I want to design the world's best submillimeter telescope. If I was to design it as big as this telescope, which is about 20 feet in diameter, it would be about twice as good as the resolution of the human eye. Now, would you guys, if you're building the world's best telescope, is twice as good as the human eye good enough?
Not quite.
Nah.
Probably not. So how do we get around it? Because there's a few things that we have to worry about, right? Like, okay, in theory, you could just make a much bigger telescope. So if you could hit ahead to the next slide for me, or the next. So here's a much bigger telescope. So here's the JCMT. It's almost 50 feet in diameter as opposed to 20 feet. So that combats it. But you get into this problem of, am I going to continue to build a bigger and bigger dish telescope? You know, there's this famous example of the Green Bank telescope that was 300 feet in diameter, raw and gusset plate, and it collapsed, right? So there's this idea that like you can continue to build bigger and bigger facilities with bigger dishes, but at some point there's kind of this like limit to how efficient that is, because bigger machines are going to cost more, they're going to expand and contract, potentially you'll have more problems. And something that we haven't talked about, which is that even though we have very large telescopes that are radio observatories, like Green Bank Observatory still, you know, operates these very, very big dishes. When you observe at much longer wavelengths, you don't have to worry about how smooth your dish is. And so submillimeter has this problem where it's like, okay, they want to achieve good resolution, so they have to have a big dish, but due to the nature of the wavelength, it has to be super, super smooth, almost as like smooth, or like similarly like the smoothness of the mirrors for optical telescopes. How those, it's more important as you go higher. As you go, I'm in frequency mode, not wavelength mode. If you go to smaller wavelengths, the smoothness of your mirrors and dishes becomes more important. So it's really a challenge if you want to work in submillimeter and you want a good resolution telescope. So the key is to do a very big single dish telescope like this, or to look at this picture or do telescopes like we have in the picture below. And so this is the submillimeter array. This was the first telescope I worked on in Mauna Kea, and it's the first telescope of its kind. Its first flight was 2003, and it bypasses the resolution limits that we have by using a bunch of little telescopes instead of one single one. And this is complicated. It's a little complicated to understand. The technique is called interferometry, but it is the reason that we were able to overcome resolution limits and take the first picture of a black hole. Think about that glowy donut of a picture, guys. We're going to look at it a little bit later. The resolution of that picture, the resolution that the camera needed to capture that image, is equivalent to being able to hold up a camera from Earth to look at the moon, take a picture, and spot a single grapefruit. A single grapefruit. We do not have telescopes that achieve that resolution alone. So it is really because of the beauty of the principle of interferometry that we're able to take pictures of black holes and maybe past that, really bypass these technological limits we had in probing the universe in submillimeter wavelengths. So thank you for letting me bog you down with details about the size of these dishes. But what I'm getting at is that submillimeter science is hard and it's very new. The first observatory of its kind that combined a lot of telescopes in an array to do interferometry got first light in this century. And now there's a very famous one known as Alma in Chile, which also observed the cosmos in an array with lots of little antennas working together, pointing at the same source, taking their images, throw a supercomputer that combines them and creates a synthesized image. And that's now the world's most powerful telescope. So the technology was developed in the 70s. And because it's so faint, because these resolution limits were hard, the other key factor that allowed this science to be possible is essentially the advent of superconducting technology. Technology that when you cool it down to very, very cold wavelengths, I'm talking of very cold, the warm superconductor work at 310 degrees below 0 Fahrenheit, and we cool ours much cooler than that. You're able to make your technology works a little more efficiently. And so it wasn't until we had these kind of superconducting elements in our receivers that essentially would allow us to amplify these very faint signals that you were actually able to do these science in the first place. And that technology wasn't developed in the 70s. So now it's like we're really in this first generation of doing this kind of science. And it's incredible how it's taken off. I feel very lucky that, within the last 5 years, I've been able to jump into telescope operations and just see how exciting it's been.
So do you think in the future people might start building these kind of array of all these submillimeter telescopes but up in space? Like, I know these
Absolutely.
are dishes, but I haven't heard of any that are up, they're always on the ground.
Absolutely. So I think it's really interesting when we talk about ground-based versus space-based astronomy, because it presents different challenges, right? Ground-based, even though you have to deal with the sphere, is so much more flexible. Humans can fix the technology. You can adapt your systems. When you send something in space, it's very expensive and you can't expect to fix it. But particularly with submillimeter, you have advantages of taking observations outside of the atmosphere. And so the telescope that is really doing this right now is, the SOFIA project that sticks a millimeter telescope outside of an airplane and takes pictures of the night sky and is able to bypass some of the moisture that we see for the atmosphere. So it's not quite fully space-based yet, but the fact that we're already seeing projects that are not limiting themselves to ground-based observations and recognize the power of interferometry, right? Like right now we are limited to making a telescope that spans the Earth. But if we're able to put things in orbit, then the resolution limits are able to be pushed even further. So I absolutely think that is the next generation of submillimeter astronomy and just in general interferometry. It's very exciting.
Well, let's hope they're a little more efficient than they are with James Webb, and we don't get those telescopes delayed.
Yes, here. So to sum up, I'm very excited and talk to you about the challenges of submillimeter astronomy. That these signals are faint, that they require superconducting temperature or superconducting receiver units, that the signal is going to get deteriorated, that the resolution is really hard to achieve. Now I want to transition. I want to pivot a little bit and talk about why it's so important. I hope to do that by talking about, please skip to the next one for me. I hope to do that by helping motivate you to talk about why the science is exciting. So I really love this image because it really highlights why we have so many telescopes, not just on Mauna Kea, but everywhere, and what we gain from having telescopes that observe the night sky in different wavelengths. So if you look at the center image of M87, this is such an iconic image of a starburst galaxy. I know you guys referenced this one in last week's show. It's really one that we love. Because we see these interacting galaxies, it's going to trigger and drive star formation in the Whirlpool galaxy anywhere from 10 to 100 times, depending on where you're talking about, right? Now, when we look at that optical picture in Hubble, well, we're seeing the very bright stars in our galaxy that have already undergone fusion, that are giving off energy in the form of heat in visible wavelengths, right? Those are the pinpoints of white light. And you can see the dusty trails, those gas trails that follow those spiral arms. But what would it look like if we start going towards more the energetic regime of the electromagnetic spectrum? Well, you can move to ultraviolet, and then you start seeing these really hot stars, and how they burn. Those are what will be a little more visible to us in ultraviolet. And then you can go all the way to the most energetic and look at these kind of gamma rays, X-rays pictures at the hottest regions of the universe and get a very different picture, right? So we can see that as we start doing images in different wavelengths, it brings out different features that are specific to interest of study for different scientists, right? If you want to understand the most energetic regions of the universe, you're probably not going to go into radio astronomy. That would not make sense at all. So let's go back to the cooler regions of the electromagnetic spectrum. Like, remember that as we go to longer wavelengths, we're looking at things in space that are colder. So moving from that optical picture, that Hubble image, which I think a lot of us are familiar with, let's move to the infrared, right? Infrared in astronomy, similar to the way that we might think about it in day-to-day life, will allow us to give us kind of these heat map images. And so in the infrared, in this picture of the Whirlpool galaxy, right, we're able to see some of these cool stars, these little M dwarfs. I love M dwarfs, that are more ubiquitous, that make up more of the stars in these types of galaxies quite often, but are cooler, right? And if you go all the way to a colder end, toward these very long wavelengths, well, then you're looking at some of the coldest regions of gas. And in particular, in this radio image, they're often looking at carbon monoxide. That's what we're excited about. We're looking at this kind of the cold dust and gas picture of carbon monoxide. And it looks very similar to this radio one. So if you wouldn't mind, can we switch to the next slide? Awesome. So this is a picture of that same galaxy using the Submillimeter Array, that telescope you saw that was made up of all those tiny little baby antennas. And essentially, it is looking at the carbon monoxide in the Whirlpool galaxy. Now, we know the Whirlpool galaxy is a starburst galaxy, that due to the fact that it's colliding with its neighbor, it is going to trigger star formation in different parts of this galaxy. Now, if you're interested in star formation, you're probably studying molecular hydrogen. But the thing to know about molecular hydrogen is that very sneaky. It's very, very hard to find. So you want to find its tracer molecule. Who is its loud friend? That when you hear that loud friend laugh, you know the whole gang must be nearby. I feel very personal because I'm often that very loud friend, if you couldn't guess. The loud friend's carbon monoxide, guys. Carbon monoxide, for submillimeter astronomers, is the tracer molecule. That if you see a lot of carbon monoxide, you're probably looking at a place of intense star formation. So I just want to look at these two. Please ignore the top image. It's another picture of star formation, but it's not of the Whirlpool galaxy. But I just want to show a different way we can image in submillimeter frequencies than this intensity mapping. But take a look at this picture. The background image is the Hubble picture. It is the same one that we saw in the previous slide. And on top of it, that kind of blue-green blobs that look almost like a topological map, that is the submillimeter emission that we posted on top. Perfect. Thank you I really appreciate the laser pointer. So we know these white pinpoints of light on Hubble are stars that are already burning. But if you take pictures in submillimeter, you're looking at much colder regions of space. You're looking at places where stars are about to start forming. Remember, think about it as like a cosmic ultrasound. And stars form from cold dust and gas. That cold dust and gas we can kind of see obscured by, or is often obscured in optical images. And you can kind of see that in this optical Hubble image, you can see this kind of brown dust and gas on these trails. Now, if you zoom in to the image on the bottom, it's hard to place a little bit, but it's like the top left-hand inner spiral it's the top center spiral. I feel like maybe you can probably match it up from each of the images. Yeah, it's like a little over to the right. Yeah, it's like this arm is what we're zooming in on in that bottom one. Yeah, you got it. I can see there's a little bit of a lag, but you can get this. Essentially, what I'm trying to point out is that place Hubble where we see this brown dusty trail is exactly where our submillimeter observation lines up. And so the way that we can understand submillimeter observation is that it's an intensity map. The places where we see green emission means we saw a lot of light in submillimeter wavelengths, but not as much as if it is yellow or if it is red. So if you look at that little red blob or those yellow blobs, ding, 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 those are likely areas of star formation. And it's happening along those dusty trails that we see in the Hubble image, which is exactly what we'd expect based on how we understand star formation. So that's something that was really cool about taking these pictures millimeter, is that it really lined up with our understanding of what we'd expect based on seeing that optical picture. So star formation, how stars form, the details, how much of certain amounts of gas, and the temperatures, and the process it takes, and how quickly it happens. That is really what a lot of our scientists want to understand when they apply for time in our telescopes. And before I go too much further, I do want to just point out something that is really cool about these kind of world-class telescopes, right? Because unfortunately, there's a limited amount of time in the year, and there's not so many facilities that can do this, right? There's only really a few places in the world that are really, really good at taking these kinds of pictures. And so if you're a scientist who wants to get time with these telescopes, you have to apply for them. And so this is something that, I think Katya can tell you about with her from personal experience. It's hard to get to these telescopes. Not to say it's Katya in particular, but astronomers know it's really hard to get time on telescopes. And it's their job to become experts at convincing observatory committees that they have this experiment idea. Because we don't have enough time to just take random pictures of space usually. We usually are going to go in, and a scientist is going to say, I really think that this star forming region is unique, and we need to study it for this reason. And they'll give some justification. And they'll put in a proposal and maybe give an idea of how many hours of time they can take those pictures. And then you have these time allocation committees that are going to evaluate it. Like, how good is the science? How feasible is it? And how much of a priority should we make taking these pictures? And that's almost always a committee that is not internal to an observatory. It's like they'll pick the best scientists, people who specialize in these kinds of observations to help them evaluate them. And then they'll rank them, and then they'll go back to their scientists who applied for time and said, congratulations, you got this amount of time, or you got this amount of time. And of course, there's always room for last minute observations. If something's really exciting happening in space and it's mysterious and we need to take pictures of it, people can always apply for kind of last minute time usually. Depending on the observatory, to get some of these pictures done. So that's just a very cool thing to learn about. It's a very democratic way, I feel like people get time in these telescopes. It's really people are always trying to do the best science most efficiently. So it's been cool to be on the other hand of that process, which is much less scary than having to apply and wait for a response, and rather getting to see the process of how we evaluate and go through these. Very cool. Let's look at some of the other results we've had from submillimeter science. People want to understand how stars form, but what else do they want to do? This next image I want to show you just because I want to put out there that even if you work at a world-class telescope, your data always doesn't look super exciting. Sometimes it looks like this. It's a spectrum. A lot of people who are using submillimeter telescopes understand the chemical makeup of different star-forming regions, of different places where planets are forming, of objects like comets. Right now, Comet Neowise is so exciting, and submillimeter telescopes are a very incredible tool to study comets for a few reasons. One, they're specialized at looking at cold objects and can study its chemical composition and makeup. But also, submillimeter telescopes benefit from the fact that, similar to radio telescopes, other telescopes that observe at long wavelengths, they can observe during the day. So they can still observe the comet even when it's out, giving them an extra opportunity to take these observations when it's really limited. You can't always get such good observations of comets that are passing through. So that is a cool thing about our telescope with respect to taking pictures of comets and how we might try to understand those chemical compositions. But it's not limited to that. A lot of the scientists who want the data that looks like the ones you're looking at, that allows us to understand how much of certain chemicals we would see. That's just a picture of some of the data and what it could look like. Not always pretty like Hubble, but still really cool science.
Right. Well, one thing in the comments somebody just brought up, because you mentioned about telescopes kind of diverting when something happens and you've got to go look at it. When LIGO detected the neutron star merger, which observatory were you at that time? And do you remember there being a big
No, that was unfortunately not something that was on our radar.
Okay.
but that is absolutely a thing where it's like there is this triggering effect from observatories where so many of them are going to divert and take pictures of something. And so I think like a really cool example of that actually is of that cigar-shaped like object, our faraway traveler, Oumuamua, I think is what it's called.
Yeah.
And when that came out, it was like I think it was discovered from Pan-Star Maui. I hope that's right. But essentially, a lot of the telescopes all pointed to look at it and take pictures of it before it went away. So there isn't this history of being able to do that. Yeah, which is I think pretty cool.
Definitely. Being able to take advantage of those opportunities when they arise, and the fact that everybody just agrees, like, that's what you have to do, is kind of a cool thing in astronomy.
Mm-hmm.
And it brings up something that I think I dismissed a little bit earlier. I think I maybe dismissed survey telescopes by saying you can't always just take pictures of the sky, but actually it's very important that we do. It is very, very important that we have survey telescopes and telescopes dedicated to surveys because it balances this need for observations, right? We are not always going to know at that time when something's exciting to look at the sky. We generally need to be taking observations of what astronomers collectively agree on are important things to be regularly taking pictures of. That is why we have survey telescopes like the Sloan Digital Sky Survey, why the new Observatory, formerly known as LSST, or even like this Pan-STARRS telescope over on Maui, on Haleakala. So I didn't mean to dismiss those. And an observatory like JCMT at the East Asian Observatory, we recognize that there's like long-term monitoring programs that you need to do. And so we actually do have a lot of programs where maybe we'll take pictures of the same region of space over time to be able to follow up on those just to see something exciting that changes. So I didn't mean to dismiss them.
Surveys are great because surveys also, they take so much data that you can't look at all that data at once. And so you just have archives of this data and people can go back years later and find something new in the data. And it's super cool because it gives a whole lot of data access for people that you can use for a very long time.
And something that's unique about astronomy is that even though there are often proprietary data limits, like maybe for a scientist that they've requested certain data sets, they get to have them for the first year, for the first 2 years, so much of astronomical observations are open to everybody. And that is something that I really love about astronomy, is that astronomy is where everyone can contribute, right? You can have a PhD and contribute to astronomy. You can be an amateur astronomer who works with variable stars and taking measures of those. You can be someone who doesn't have astronomy background but loves coding in Python, and you can download your Hubble data sets and start doing some data analysis of things, right? Like it is very much a field that is open to all, and I think that is like something important to maintain as we move into this next generation of observatories, of surveys, right? Like there's so many more discoveries that have come from archival data. So what can we do to keep making data open and providing more data and making it easier to use? Because that's only going to accelerate our understanding of the universe.
Exactly.
Most definitely.
Yeah.
And I think that's also like one of the criteria that time allocation committees look at when looking at proposals is what is the benefit of this observation for long-term and archival research?
Totally. And it's a challenge, right? Like we are entering an era of technology where handling big data is difficult. So how do we keep allowing for archival data to be stored properly so that folks can benefit from using it and like mining it in the future? And that is actually, it brings us to our next slide, if you wouldn't mind advancing one, because Alma Observatory has a huge potential, like has a huge problem, but it's a challenge for how they maintain their data. So the telescope that I worked for prior to working for JCMT was the Smithsonian Astrophysical Observatory Submillimeter Array. We saw some pictures of it. That was that tiny little satellite-looking telescope that is, there's 8 of them and they're each 20 feet in diameter. Alma, here you can see a picture of some of the Alma array. So many antennas, right? And so it's able to achieve much more resolution where essentially interferometric arrays, I don't know if I emphasize this enough, we'll talk about this a little bit more when we're talking about the Event Horizon Telescope. But, you know, before we were able to have interferometry, this ability to combine the data from lots of little dishes, we were stuck with the resolution limits of essentially making dishes bigger and, you know, choosing to observe in wavelengths that are smaller to make that ratio between wavelength and the size of your dish a little bit more favorable to getting a high resolution picture. Now we know we can bypass that. We can instead kind of trick the system. We can take pictures with a lot of telescopes, and then we can send that data to a supercomputer, which combines those interferometric images and produces an image that bypasses that resolution limit. So now you're no longer limited by the size of the dish itself, but rather the size you can move them apart. So take a look at this picture of Alma. Do you see how there's some dishes which are very close together, like at the very center, and some that are very much further apart? This gives Alma a very, very unique advantage because the telescopes that are pushed together are able to probe the large-scale structure of an object versus the telescopes that are far apart push that resolution limit, allowing it to see unparalleled detail. And the result of having so many dishes doing that is like this image that we have here, which I think is one of the coolest images. And what we're looking at right now, if you haven't recognized it, is a baby solar system. All right. These are planets that are in the stages of forming. And what we can see are different dusty trails that eventually are going to be cleared out as a result of the disk rotating, as a result of gravity, essentially just doing its natural processes, essentially collecting more and more matter, building gravitational pull. And essentially planets are going to form in all of these trails. And you can see that the dusty trails are distinct, right? These are going to be where the future orbital paths of however many trails you can count there. This could potentially be a solar system very similar to our own with, something on the order of a dozen planets, right? And so this is just a really incredible picture of this is our cosmic ultrasound of a solar system. Really, really cool.
Two questions for you.
Yes.
Oh, so in this image, right? So if we take pictures of these like protoplanetary like disks and solar systems, we can actually predict.
Yes.
Yeah, we can actually predict the number of planets that will arise from that disk, like just by counting the rings.
Yeah. It's hard to say, like you can't direct correlation, but essentially what they are thinking is that those are going to continue to be ones where they would see planets clear them out and form. Is it going to be exactly those rings? Maybe not. Maybe some of those, that process could be disrupted. Maybe some of those potential planets could smash onto one another. Maybe it'll be more turbulent and some of those would combine with a much bigger planet. And this is my rudimentary understanding. Of course, we could go to the scientists and have the exact nuanced understanding. And this is still very new. But that is what we were thinking. That is what we are thinking is we finally have the resolution to be peering in close enough to these solar systems in formation that are getting us closer to that detailed understanding of us being able to essentially count rings and get to planets. Yeah.
Awesome. Also, in terms of the array, so you're talking about how you have some that are really close together and some farther apart. What is the system that they use to decide where exactly to place all of these dishes? Because in this case, it doesn't look like there's any symmetry or organization to how they're located.
I love answering this. Okay, yes. So something that's actually pretty unique is that it really depends on the kind of science you'd want to do. And the science you'd want to do depends whether you want to use a single dish telescope or an array telescope. And for example, the submillimeter array that I used to work at on Mauna Kea, it can have different formations. So the telescopes can be as close together in what they call subcompact, that if you tilt them towards the horizon, they crash into one another. And they can be separated up to half a mile apart. And so each semester, essentially, they move the telescope into different configurations depending on the science need. If you have a science goal that requires you to probe the large-scale structure of an object, you want to use a single dish or an array where the distances are minimized. If you want high resolution, you're going to have to pull them much further apart. And so often what you'll see is that maybe a science result will compare or they'll combine imaging techniques from different telescopes. Maybe they would use our telescope JCMT, because it's a single dish that could probe something, and they'll complement it with SMA, submillimeter array images to get that high resolution detail. And so it really depends on what your science goals are. And different arrays, different techniques for what they think is best for the distances between them. So if you look at a picture of the very large array in Socorro, New Mexico, very long array, VLA, feel silly that in this moment of being on TV, I forget if it's long or large. But
Large.
the VLA, large, very large. That's what I thought too. But I thought very long felt very silly, and then I was like, there's an extremely large telescope, so I can't discount silliness of astronomy. But if you look at a picture of it, it's distinctly like a Y, where they have the same distance between the telescopes, and that is essentially just a 6 of one, half a dozen of the other, in terms of how, my understanding how you're going to reduce the data later is that at the SMA, they made a very specific design choice, so you don't have any overlapping baselines. And that's what they call a baseline, is a buddy system between one antenna and another. And like I said, the length of the distance of the baseline determines the resolution of your image. And so the SMA made the decision that there's not going to be any overlap distances in baselines, because that allows you to probe each baseline resolution differently. But you know what? Maybe you can make the choice like VLA did and have all the same ones at the same distances, because then you're essentially increasing your telescope power at that specific resolution. So maybe you're not spanning as much of a resolution range, but you're getting more of them at that resolution. It's kind of a choice a telescope can make that can have different advantages depending on the science you're doing. All this is to say, the spacing between your array really depends on your scientific goals, and different observatories are trying to support those goals in different ways. And wait, something that I feel like didn't go into the details of this, but the reason that we're able to essentially take advantage of this is that we can kind of fake the system by using interferometry. We can stare at an object and essentially stare at it long enough that the Earth rotates, and it can fill in a synthesized dish. And essentially, all of this depends, essentially what I'm saying, on taking very long observations. So even though it is a very big telescope, you can tell that these dishes are spread out and they're over a very big period. The resolution is determined by the distance between the two. But imagine that if you took a snapshot of a telescope that is like, if you could make a zero or would you mind with your array laser pointer, like make a ring around all of the array? Like those outer dishes allow you to take a picture with that resolution, but because there's so much space in between all those dishes, you have a very low sensitivity. Like you're not capturing any photons. So what do? Like what worth is an image if it has high resolution, but very low sensitivity? Like you don't capture many photons. It's not that useful. What do you do if you're trying to increase your exposure for any optical device, any camera? A lot of you guys who are on here right now, what do? Like if you want to take a picture that's too faint of some cool nebula.
Anybody in the comments want to chime in?
Don't be shy.
Like, I get a really good picture of the Orion Nebula if I only let my exposure be 3 seconds or like half a second.
I'd probably go a little longer than that.
You go longer. That's what I'm getting at, is for very faint objects where you need more photons to increase your exposure time. So often for these projects with arrays, even if they have a very high, they are able to achieve these resolution limits, they'll take such long exposures that the Earth will rotate, and they will take that into account in their imaging. So they'll take a picture for like 8 hours, have the dish rotate, and by that time, it's like, this is a hard thing to do without a picture. I didn't unfortunately provide one. It's like, it's as if it's filling in the synthesized dish. It's like adding more dots to a picture. How would I phrase this? I'm sorry, guys. My analogy is not so good. I guess imagine creating a picture of a ring, like if you were tracing around the edge of Alma, of that array right there. If you can't add more dishes, you can just keep taking pictures for longer and make up that sensitivity somehow. And so often these arrays take really long exposures to make up for the fact that even though they're high resolution, they don't have a lot of photons captured. So
the longer you leave it on, the more photons you get in your light bucket.
Exactly. And they really, really want a lot of photons, and they need to make up for the fact that they have high resolution but small buckets, only a few buckets representing for each one of these antennas. Yeah.
Yeah.
So I I know. Thank you so much for bearing with me by being so excited about these geeky little details about resolution and about the arrays. I'm sorry if there's anything that needs further explanation, always chime in the comments, and you can feel free to interrupt me. But we can also really look at a couple other images that I really like of some cool discoveries.
Yeah, let's highlight a couple more, and it's already 9 o'clock, so we'll highlight a couple
Okay.
more.
I'm gonna highlight this one, and then we're going to black hole.
Okay.
I'm so sorry that it took so long talking about all of our other things. But this one is just, I love this. Really quickly, what happens when a comet crashes into a planet? A lot of people tried to study this when Shoemaker-Levy hit Jupiter in the early 90s. And what was cool is that this picture was taken by the SMA a decade later. And essentially what they found was the hole created by the comet allowed all of these elements from the upper atmosphere to be released. And 10 years later, they saw that Jupiter must have strong polar downward vortices because all the hydrogen cyanide got pulled down to the South Pole. And so there must be some really cool meteorology happening on Jupiter. That's it for that one. Let's talk about black holes, and you guys have really bared with me. This picture looks like what you saw in Interstellar, right? It looks like some sort of weird glowy ring. We can see that essentially it's going to be redshifted. This is it's like there's going to be some that is going to look darker and some that's going to look lighter, and that is kind of a result of the fact that it's some of it is moving towards us and some of it's moving away from us. And this is kind of what we expected to see. This was a model, right? So how did we do it? Well, I talked your ears off about interferometry, about the fact that if we can pull dishes really far apart, we can bypass resolution limits and get a really, really high resolution telescope. So look how far we pulled them apart, all right? You can see where I am if you go all the way to the left of the image and see the JCMT and SMA. Those are the pictures we've been seeing. This is in Hawaii. And here are a few of the others in the world that we're able to do submillimeter astronomy. So these are also places that are really high in elevation and really, really dry conditions. This is the South Pole with the South Pole Telescope. This is Alma in Chile that we were just looking at this picture and doing this very long, convoluted explanation of interferometry. You can see that we have the LMT. You can see we have the SMT back on the North American continent. And then you can see we also have some over in Eastern Europe. And essentially you can see that it's only half of the Earth because only half the Earth can see has the same source up at the exact same time. And we were able to do these really exciting observations that were released in 2017. And so let's skip ahead to this next slide and take a look at the results. Here we are. Here we see Povecchi. And so this was released in 2019, in April 2019. But it took a lot longer to do these observations. So I'll tell you a little bit about the history of this, and then I'll talk to you about the process. And that'll be just a few minutes, and then we'll just turn it over to questions because I've talked at you guys for so long. Thank you so much.
But we already have one request for you to come back.
I think we need to do a second show. Yeah. Where you're going to have to come back.
Guys, I love this. We can talk, definitely. So let me just tell a little bit about what went into taking this picture, and then I'll tell you about where my role came in, because all these things we're talking about, right, I'm talking about as someone who gets paid to play with telescopes, and because of that, I'm very close to the science and get to participate. But there's so much that we could talk about all of these. So the first ideas for this came about in the mid-2000s. Essentially, these scientists wanted to see if it was possible to bypass resolution limits, take pictures of the edge of a black hole. And so they first did this back, I think, 2007, 2008, 2009. They linked up telescopes with like the JCMT, and there was a Caltech Submillimeter Observatory with telescopes in California. And they came back with an image and they're like, okay, we need to get way more computing power. We got to get way more telescopes. We got to get a way higher, way better resolution. And so we did the first test run in May 2016. And it's so exciting, guys. It's like all these observatories need to make sure that all their instruments are working. They have really great weather. And it's extremely important. This is a very coordinated campaign. Because at the end of the day, right, you need to kind of work the system so that when you're looking at your data, it thinks all of the images were happening at the same exact time and can be properly combined. And so that requires extremely precise timing. We invested in a very expensive hydrogen maser because we need better better timing keeping for all of this, it requires a very powerful supercomputer and a lot of coordination. So all of these images were taken without knowing the experiment would work. We took our images, we hoped that we would send it off to the supercomputer and get a result we were happy with. So we did a test run in spring 2016 that went really, really well. And essentially you open up 10 or 12 days for all the observatories, and then the head of the campaign sends out a call saying we're on or we're off, depending on is there good enough weather and are all the instruments working at all the different sites around the world. And then you have a very specific schedule for what times you're supposed to be on what calibrators, on what objects. And of course, that's different depending on when your source rises and sets, which depended on which location you're at. And so we took pictures of 2 black holes and also some calibrators. And the first results were released in 2019 from the 2017 campaign. And that is this picture we see here, this real exciting supermassive black hole in M87. So this is much bigger than our own supermassive black hole, fondly known as Sagittarius A star, but it is much easier to observe for a couple of reasons. So this is a much bigger black hole. It's 1,000 times more massive than that of our own Sagittarius A star at the center of our own Milky Way galaxy, and it's much, but it's also much further away. But the fact that it's much bigger meant that it was a little bit easier to observe because of the nature of the rotation of the black hole. Essentially, it's rotating a little bit less fast. And so we had this ability, it's like a layman's terms to say it, but it's like, it's so hard to take a picture of a really fast athlete, but a slower one, potentially you'll capture a little less blurring effect. Essentially, it was a little bit easier to reduce the images for M87 versus a smaller black hole like Sagittarius A star. And it just is so exciting because, guys, you saw Interstellar, you saw that model we saw in this previous image. It looks so similar. And to prove that it was that similar, there was a lot of things that were done that was really, really cool about the Event Horizon Telescope. So what they did essentially is they had 3 separate teams analyze the data, and they took 5 nights of really good data. And they each analyzed 3 separate teams did each night individually, and they all came up with extremely similar results. That shows how robust they feel it is. And what you're looking at, something that was only achieved because we had these high resolution observations, equivalent of that to being able to spot a single grapefruit on the moon. And I really like using this XKCD cartoon just because it shows how big it is. It puts in perspective, right? So it has our solar system overlaid. You can see at the center that where the orbit of Pluto would be. And you can see that, the object we've sent furthest away in the 70s, the Voyager, is essentially getting towards like the edge of the radius of this supermassive black hole. So this is a huge object, compact, of course, because it's a black hole, but a huge object. So I feel like, I had a very small role in the Event Horizon Telescope just by taking their images over the course of 3 years. But it is so inspiring to be part of something that required so many hundreds of people and so many thousands of hours of work. And it really gives me faith in humanity that we can achieve a lot. So I want to talk about this other result that came out more recently from the Event Horizon Telescope. And this was actually on Quasar 3C279. So quasars, right, have one of these really bad names, similar to like nebula, where astronomers gave it a name, or a planetary nebula. Astronomers gave it a name not knowing what it was. So a quasi-stellar object. Essentially, there were these objects that were extremely bright in radio frequencies and non-visible, non-optical frequencies. Quasars are host of super active galactic nucleus, like really, really powerful turning black holes, supermassive black holes. And so 3C279 was a calibrator. Like this is what we used just to make sure our observations were looking good. But some scientists actually took some time to look at them and look at the relativistic jets, and they found something really weird. Like you would assume that these relativistic jets would be directly proportional at the base to the how would I phrase this? To the plane of rotation. That is like what we'd imagine. Like you see jets coming out directly from the black hole, and so that's what you would imagine when you look very close at them. But that is not what we saw. We see these kinks in these jets, these sideways kind of turns and kinks, which suggests some different structure, which is still kind of unknown to scientists. And we had never had details of the base of these relativistic jets coming out of these supermassive black holes, these quasars, seen before in this detail. And so it kind of is posing a challenge to how we understand these kinds of jets that are moving at 95% the speed of light.
So your
That's the
calibration
cool
data
thing is
ended
that-
up providing you with creating another kind of mystery.
Right, which is so cool and reminds everyone out there the pictures that they think they might throw away or just use to make sure things look, hunky-dory could be really awesome to understand something later on. Don't discount them. And the other thing which I think is exciting about this is like it's starting to show what other opportunities we have with ultra, ultra, ultra high resolution observations. Yes, at this point with the Event Horizon Telescope, the kind of pictures that we take, it's not realistic to do these kind of huge campaigns where everybody has to get on at the same time. There has to be a call for every kind of science yet. But the fact that we were so quickly moved within this field of submillimeter astronomy to, in 2003, building the first array dedicated to the cosmos in this light, to then having Alma within our, more recently, be the most powerful telescope in the world, to then being able to have these really incredible results of high resolution of this black hole. This happened so quickly, guys. It really gives me hope for, or makes me excited about what we're going to see in the next 25 years. Because if we have this resolution power for these frequencies that we haven't used to probe the universe fully, what else are we going to find that surprises us? We were surprised at how these relativistic jets looked. What else is going to be exciting to us? So that is like the end of my spiel. I'll take some questions. But I just hope that I was able to convey to you how exciting astronomy is and the kinds of exciting science we might be able to achieve with it in the future.
Definitely.
Yeah, I don't
now
think
I'm excited.
Yeah, I don't think anybody's coming away from here not excited about submillimeter astronomy. I think the only downside is nobody can go do it as an amateur astronomer.
Exactly. But I don't know if you guys have heard of this. There are ways to do these kinds of radio astronomy in general and radio interferometry even. And I don't know if you've heard of these kind of radio Joe projects, but something that is very cool about radio astronomy as opposed to, I think, optical astronomy is that anyone can build a radio receiver. Anyone can build something that we could point at Jupiter or the sun and pick up these kind of radio frequencies. And in some ways, because you don't have to have really nice, smooth meters, like with optical astronomy, we can pick up the supplies at Home Depot and start taking radio observations. The only thing is it's just not as exciting, in terms of sometimes maybe not as exciting a picture that looks like Hubble. I sometimes think that radio images look like someone sneezed onto a page. It's like my friends at Gemini or at Keck have these like really pretty space screensavers, and I'm like, look at this blob, guys! This is the coolest blob. Look at the shape of this cool blob. But just because I feel like they're a little less exciting, or a little less interesting to look at, doesn't make them any less exciting to me.
What do you think is the future of submillimeter? Like, what do you think is going to be the next, I guess, kind of big thing that we're going to use it to observe?
I think that the future is going to rely on, in some ways, doing this kind of submillimeter interferometry in space. I also am very curious to see how submillimeter astronomy extends beyond star formation, because I think that has really been the bread and butter of this frequency space of trying, because due to the nature of the frequency, we're looking at cold, dust, and gas. So cold, dust, and gas makes up so much of the universe, and those planets are going to form, those stars that are going to form. But I also think that we have these really interesting capabilities to do these kind of far infrared temperature mapping and these kind of opportunities to do these chemical compositions of different celestial objects that, I don't know, maybe we'll have new applications in the future for it. I just really feel that it's so young that we don't know its limits yet. So it'll be exciting.
Well, I can't wait to see what we find out next. But I just want to thank you again for coming on our show, and taking this time to talk to us. Clearly, an hour is not long enough to actually talk about submillimeter astronomy.
I'm so sorry. In my mind, I was like, I'm going to have this be a nice 50 minutes. But, once you get me talking about this, sometimes I just can't shut up. So thank you all so much. And also remember, just because we're signing off now doesn't mean the opportunity to ask questions is gone. So feel free to comment below or share any questions you have. And we'll find a way to get the answers back out to you. So thank you everyone who joined in. Thank you so much, Adam and Katya. I had such a blast with you guys tonight.
Thank you. This was fantastic. And I am 100% sure that we will be hosting you again on our show at some point in the very near
And I'm hoping
future.
that maybe I can also bring on some scientists. I can share some science with you who will continue to give you more reasons to learn more about submillimeter and radio astronomy.
Yes, that would be awesome.
Awesome. Thanks, guys.
All right. Thank you, everybody. And hopefully we'll see you guys again next week. And again, we get another person telling you that you need to come back. So hopefully it will be sooner rather than later.
Mahalo, guys.
Good night, everyone.